I'll be talking to you about some introductions to the muscular system. So the muscular system and its purpose is really to generate internal tension. So it does that by it manipulates the bones and the ligaments and tendons and everything else to help us produce movements and locomotion and all these different things. So the muscular system plays another part or assisting part with the nervous system in order for that to happen. I'll get a little bit on in this PowerPoint on how the nervous system produces muscular tension. So 3 different muscle types we're going to go over really brief because my screen is not in the right spot. Hopefully that's a little better. 3 types are going to be skeletal predominantly. We're also going to talk briefly on smooth muscle and cardiac. Okay, so smooth muscle is located on all the walls of the blood vessels, internal organs, and that is actually a muscle, and it does vasodilate and constrict, which means it goes from its normal resting diameter. Okay, so it's a vasodilation, expands, and vasoconstriction actually gets smaller. So this happens a lot, predominantly controlled by the autonomic nervous system. For example, when we change postures, when we get up, there's usually some type of vasoconstriction that happens. That way we don't get super lightheaded. Some of you guys may experience that where you get up too quickly and you get really lightheaded. You gotta sit back down for a minute or so, and that's just for whatever reason your blood vessels didn't vasoconstrict fast enough to take into account that change in positioning. Extreme cases is actually a form of shock in that regards. So all these like smooth muscles, obviously they're involuntary. We can't control them. It's just aka automatic, and it's on to our change in lifestyle, pace, posture, all those different things. Cardiac muscle, okay, also like the heart is also called myocardium, is involuntary, controlled by the autonomic nervous system. The heart can beat for the most part without an electrical impulse from the brain and central nervous system to a very small extent for a very limited amount of time. But the heart is very resistant to fatigue. It is always under stress. It is always working. Okay, the heart never really gets a break. Okay, it also has a ton of mitochondria, as you see in the picture on the right, to help produce all this prolonged muscle contractions, okay, aka heartbeats. So the heart muscle is a little different. It's more the cells are kind of intertwined and tangled. Okay, and then we have a lot of intercalated discs. Okay, so this enables a coordination of the adjacent cells. That way, a contraction occurs. Okay, most of the heart contracts at the same time. Okay, not really at the exact same time, but in almost like a wave. Okay, that way we can produce this heartbeat. Okay, so now getting more to the skeletal muscle. So skeletal muscle, okay, is voluntary control. For the most part, we can control all our muscles for the most part, or the muscle regions. So all muscle we talk about is the skeletal muscle is attached to the bone via usually a tendon. If it's not attached to the bone, it's attached to some kind of other like aponeurosis or some other really thick, hard connective tissue. Okay, but for the most part, all muscle connects to a bone via tendon. Okay, so there's tendons on both sides of the muscle. Okay, right with that muscle belly right in the middle. And when that muscle goes through a contraction, whether it's concentric or eccentric, which we'll get to that here in a little bit, tension is produced. Whether it's tension during a lengthening, eccentric, or tension during a concentric, which is a shortening, okay, tension is still produced. The breakdown in some of it, so if you look on the picture here, I'm going to go a little bit of a reverse order. Okay, so we have the myofibrils, okay, located here, and these are more like the single muscle fiber, okay, if you think about it. So that is covered by a connective tissue called the endomysium, okay. So that, you see kind of interchangeably here. So this endomysium, okay, covers all that, and that kind of connective tissue It's thin. It's like a sheath. Kind of keeps it separated from all the other muscle fibers. And that way, if like a group contracts and another group doesn't, okay, they're not stuck in one another. Okay, so it has a little bit of a separation for things to occur. That endomysium, as well as all the other fascias, we'll get to it, helps separate, and it is usually pretty thick and strong. And as we kind of get up to like the whole muscle and the fascia covering that, it gets significantly stronger. Okay, so then we have from the individual muscle fibers, okay, then we have the fascicles, which is then a group of muscle fibers, okay, kind of together. And so that fascicle you see here, yeah, showing up, okay, this whole thing here is separated by perimysium, okay. So that perimysium, okay, is here, keeps all these different things, these bundles of muscle fibers kind of separate from one another, okay. And then that perimysium is covered by the epimysium. Okay, epi usually means above if you've taken medical terminology, or above or around. Okay, it covers that entire muscle in this fascia. So fascia is this really kind of thick connective tissue. We've all seen it. We just didn't realize what it was. So if you ever eaten like chicken or steak, and you kind of ripped apart maybe that fatty edge from the rest of that steak, for example, and there's this really thin, almost like a white spiderweb-ishy tissue, okay, that's fascia, okay? It's all throughout all our bodies. It keeps our organs in place. It makes sure like things don't fall and move when we change positions, or move or fall or run to a wall or whatever it is. It's pretty thick. It's really strong. For the most part, in this case, that fascia, okay, goes up and becomes that tendon. So tendon is a form of a fascia, okay, really thick, strong connective tissue, and that attaches to the bone, okay. And that tendons are very, very strong. And other PowerPoints I'll get into more in depth on more of what that tendon does, and prevention and injuries and stuff like that. But that is kind of breakdown of all the muscles. Okay, so the control elements. Okay. So let's get everything on the screen. Okay, so we have a sarcomere right here. So a sarcomere, I can't talk today. That is a small section of that myofibril, that muscle fiber. Okay, so all these stacked one another makes that huge long myofibril, or that muscle fiber. Okay, so Z line to Z line, as you see up here, is one sarcomere, okay, per muscle fiber. Okay, and on this sarcomere, we have actin and myosin. So actin and myosin are these contractile elements of that muscle, where when an action potential, and we'll get to that slightly towards the end, or that electric signal is sent via the nerves to the muscle, okay, these actin and myosin, okay, so we have the myosin here, these almost like a tree-like structure, okay, and these heads kind of go out and they grab different parts of that actin, okay, and then they either pull or push, and as they pull, okay, you see there's a tree on both sides here, so let's say they're both pulling from both sides, okay, well now that those Z lines, okay, on each side are going to get closer together, okay, resulting in that whole muscle fiber, okay, shortening, okay, or we have that shortening of that muscle, okay, overall, and we see that contraction. There can also be a, let's say these actin and myosin, let's say they push out, okay, instead of pull in, and so now we have the lengthening effect. So those Z lines are now getting longer, and so that muscle is now lengthening. Okay, both do require energy for this. So it's not like when muscles are resting, it's lengthening. There is some kind of action with all lengthening muscles as well. So that is how muscles shorten and elongate, is this actin and myosin, okay, and they're very, very small, obviously, okay, because that's a very small section, okay, of the myofibril or muscle fiber. So when that contracts, either shortening or elongating to produce that tension under load. Okay, now there's a lot of different muscle fiber arrangements out there. I'm going to cover over them pretty brief. Okay, let me move this over a little bit so you can see this picture a little bit better. Okay, so 4 different types of muscle fibers. We have the circular, okay, as we have here around the mouth. In this ring, we also have it in our, call it posterior sphincter. So when that muscle contracts, that sphincter, okay, gets smaller. Okay, there is some kind of constriction that occurs. So either it's our mouth going here, okay, so that is that getting smaller, or in terms of our anal sphincter, okay, that is also getting smaller to restrict any gas or solid matter from exiting. Okay. Next we have the convergent muscle fibers arrangements. Okay, and so this one is common like on the pectoralis major. Okay, where you have this big muscle that attaches to the whole part of the chest, and it converges down into one single point on the humerus. Okay, that is an example of a convergent muscle. Okay, can contract pretty hard. We also have parallel muscle fibers. Okay, so the fibers run very, very parallel to one another, especially in they run parallel in the force of production. Okay, for example, for that one, okay, we have our sartorius, this muscle right here, which is located right in here. It's kind of like a weirdish muscle to where it's not a hip flexor, it's not a quad, okay, it's not a groin, okay, or external rotator, but it does a lot of those different motions together. It does like hip external rotation, hip flexion, and knee flexion all at once. Okay, not a prime mover, but it does do a lot of stuff. Okay, then we have, oh yeah, cover the parallel. Let me move on to the next slide. Move this around the screen a little bit. Okay, then we have our pennate muscle arrangements. Okay, so pennate, and it can be broken down even further to unipennate, bipennate, or multipennate. So the muscle fiber arrangement is not parallel to the angle of pull. Okay, it could be a diagonal, okay, 45 degrees sometimes. So this is like a unipennate, okay, like the flexor pollicis longus muscle. So if you don't know, that is the muscle that flexes your big toe. Okay, and so what happens with a lot of this muscle fiber arrangements, okay, just off to the side, is you can generate a substantially larger force production than like a parallel muscle would. Okay, you don't have the quite range of motion that parallel muscle does, but you can generate significantly higher forces with this. Okay, for example, that flexor pollicis longus muscle helps us generate force or locomotion, okay, at that toe-off stage of like the walking gait. So that last little bit when you're you're pushing off, okay, it's usually generated through your big toe. Okay, then we have bipennate muscles. Okay, so this one is our rectus femoris, as in being here. Shouldn't be. Your rectus femoris is one of your quad muscles, okay, quadriceps muscles. It is also one of your hip flexor muscles. Okay, so it has to generate a significant amount of force during motion because that is one of your prime movers. Okay, so we have two heads, as you can, I guess, picture it. Okay, on both sides. Okay, and lastly, these multipennate muscles. An example of that is, see here. Sorry, little things in the way. But example of that is like our deltoid muscles. Okay, so our deltoid muscles here, we have an anterior, middle, and posterior sections. Okay, it's all the same muscle. Okay, they're not different muscles, but usually all of them contract at some point. Okay, for production. So if I'm doing shoulder abduction out to the side, okay, my middle deltoid, okay, as well as my anterior posterior are all contracting for that. Okay, but if I do shoulder flexion up here, okay, my anterior deltoid is predominantly contracting. My middle, probably a little bit. My posterior deltoid in the back, okay, is probably going through a contraction as well. It's more of a eccentric contraction. Okay, that's a lengthening of that muscle. Well, the anterior deltoid is doing a concentric contraction. Okay, that also allows on the deltoid for us to do all these other different motions. Okay, horizontal abduction and adduction. Okay, well, it's all that same deltoid muscle. Okay, just different sections are under different loads at different times, whether I'm anterior, middle, or posterior. Okay, skeletal muscles have four characteristics. Okay, they have a contractibility. Okay, which is the ability to be tightened or contract from an elongated position. Okay, I'll get all these a little bit more in depth. So excitability, okay, readiness to respond to various types of stimuli. Okay, for example, irritation, okay, or electrical stimulation. Okay, we have extensibility, a ability to be stretched. Okay, we have elasticity, ability to return from that now stretched or lengthened position, okay, back to its normal relaxed spot. Okay, so extensibility, okay, ability to stretch, okay, usually does have a max length with it. You can't alter that max length. Usually some kind of stress under time, okay, aka stretching over like long periods of time, not to a substantial like difference. Like someone's trying to become more flexible, they're not going to have a super intense change in that max muscle length, okay, even long term. It's a very long term stretching to see a substantial change in that. Okay, you might have a little bit of that muscle change after some light stretching, okay, but to truly become more flexible, you need a substantial adaptation to that muscle in terms of its length. Okay, elasticity, okay, able to return to its normal length when relaxed. Okay, so that can store that kind of kinetic energy, okay, during that. But usually that muscle is going to go back, almost like a rubber band would. Okay, still stores all that kinetic energy for it to be used for the next motion. So like when we jump, okay, if we take a 1 or 2 steps into our jump, we can help build up that kinetic energy to jump higher than like a standing high jump would, or broad jump. Okay, usually 1 or 2 steps can help us hold that kind of energy, okay, to release it more intently. Okay, excitability. Okay, this is a big one. So ability to respond to stimuli. Okay, usually delivered from a motor neuron. Okay, so that is the electricity component. Okay, so or chemistry, however you want to break that down. So when that motor neuron is, or that's that nerve that innervates muscles, okay, is sent to that muscle, it excites it. Okay, and that excitability, okay, triggers an action potential or just that muscle to actually respond in some kind of and produce some kind of stress. So that excitability for that produces movement. Okay, and so it can be excited through electrical stimuli, like we can put electrodes on us, okay, in a certain amount of electricity, okay, and actually will produce that muscle to fire. And we can help retrain muscles or use that to help relieve muscle spasms. And there's a number of different ways that you can use electricity to affect that muscle, but getting more onto terms of like muscle recruitment. Okay, so like in the picture here on the right, that is a motor unit. Okay, so motor neurons, okay, or that nerve that innervates muscles. Okay, so that motor neuron comes out and then it branches out to all the different muscle fibers in that motor unit. Okay, so that motor unit can vary from 300 muscle fibers to 2,000 to maybe even greater. And the pros and cons to the different sizes is if it is usually the smaller the motor unit, the more sensitive or precise the task is. Okay, so if like writing and like vision is very precise, like movements, okay, are going to rely on smaller motor units, okay, versus once we get to the bigger motor units, okay, like predominantly in the force producing muscles, like our major muscle groups like quads and glutes and all these different ones, and that produces more strength and force production than these smaller units. So recruitment is utilizing more motor units to do the required task. Because let's say you contracted a muscle, okay, or let's say I was picking up this marker, okay, and I was doing a bicep curl with that to pick up the marker, okay. I don't need a ton of motor units to pick this up because it's relatively light, okay, to oppose gravity and the weight of my arm and everything else, okay. Just for simple sake, let's say I use 10 motor units to pick this up in my bicep just to contract it, okay. If I were to pick up a 50-pound dumbbell, I may be using 300 motor units, and each of those motor units could innervate, I don't know, let's say 500-600 muscle fibers. Okay, so now I have substantially more motor units, okay, which is bringing more muscle tension to oppose a greater amount of resistance. Okay, so the heavier the object, okay, the more motor recruitment you have to use, okay, to recruit more muscles, okay, because we don't contract 100% of our muscle fibers. Okay, there's very, very specific situations that we can, and when that does happen, our muscle production can be so intense that it can actually rip the tendon off the bone, or actually break the bone, if everything were to actually contract. And there's very few cases where the human body, usually the fight or flight mechanism, has to kick in, and some other examples for this to occur. But that is so that recruitment is how we generate more force for lifting or doing different tasks. Tendons and ligaments, as I mentioned earlier, tendons attach bone to muscle. Okay, ligaments, on the other hand, attach bone to bone only. Okay, there's no really exception to this. Both tendons and ligaments are made of thick connective tissue, okay, and are able to withstand enormous amounts of tension. Okay, I mean, they're measured in tons for different things. I believe off the top of my head, and don't quote me on the accuracy of this, like when we're changing directions, like during a sprint, that cutting force can generate 4 tons of force through our patella tendon in our knee, stuff like that. So, and these tendons and ligaments can adapt over time through the forces placed on them, obviously, whether that's weightlifting, just normal like stress under tension of whatever activity we're doing, whether it's running or jumping or whatever it is. Okay, our body will adapt. Okay, and in terms of just the tendons and ligaments alone, okay, they will become a little thicker, and they'll become what's the terminology? I think thicker is the actual terminology that they use for it. Okay, and will withstand more force. Okay. Okay. A rigid insertion and the muscle belly of the muscle. This is just a quick breakdown of most of it. So the origin, you may see this in some texts, usually refers to the more proximal end of that muscle where it attaches. Okay, where like the insertion is the more movable side. Okay, which is usually distal. Okay, and then the muscle belly is obviously right in the middle. Now the length of the tendons on both sides can vary a lot. Okay. For example, in the hip, I don't have a good picture, we have the tensor fasciae lata muscle, okay, which is pretty much like right where you put your hands in your pockets, okay. Like in me, it's probably about that long, okay. But the tendon that attaches to, okay, is the IT band, okay, which is a tendon in itself, which that one's probably a foot, 12 inches on me, okay. So that form of that tendon is significantly longer, okay. You can also have depending on how many heads of that muscle you have. So like, think about the bicep and tricep. Okay, so bicep has 2. You think bicycle has 2 wheels. Okay, biceps brachii, okay, has 2 heads. Okay, so we have 2 heads up here. So the bicep has 3 tendons total. Okay? Tricep has 3 heads. Okay, because there's 3 heads of that tricep muscle. Okay. And lastly, I'll finish up on this PowerPoint some different muscle actions. I use some of these throughout this whole presentation. But just so you know, so we have, in terms of like deltoid, okay? So this is isometric contraction, or that muscle is under load, but there's nothing really happening, okay? For there, and I'll come back. So a concentric muscle action is a shortening of that muscle. In this case, that deltoid muscle is shortening, okay, to lift the arm, okay? Where down here we have the eccentric muscle action. That is a lengthening of that muscle, okay, in order for me to adduct my arm again. Even though the arm falls, the muscle still has to go through a muscle contraction, okay, in this case eccentric, to slow down the arm. Okay, so that antagonist muscle, okay, in this case, is slowing down that extremity. Okay, excuse me. And so here's a probably better form of isometric contraction. So if you're like a mini squat, okay, and you can feel that muscle over time start to burn, okay, that's because it is contracting to make you upright. So an isometric contraction is a contraction, but there's no movement occurring. Okay, so because the hamstrings here is being opposed by like the quads and the glutes and all these other supporting muscles to keep you from moving, it is still under stress. Okay, so that's called an isometric contraction. Okay, so when you're squatting down, so the downward motion, okay, in terms of your hamstring is going through an eccentric contraction. Okay, and then when you're standing up from a seated position, okay, your hamstrings are going through a concentric contraction, okay, because they are shortening during that. Okay, it's just a little breakdown for that. And I believe that concludes my muscular system. Thanks for watching my TED Talk.